Konnichiwa, gozaimasu. PyCon no minasama, hajimemashite. Luka to oimasu. Dozo yoroshiku o negashimasu. Okay. So I'm afraid this is as far as my Japanese goes for the moment, so the rest of the talk is going to be in English. The title of my talk is Why You Should Care About Types and How Do You Use Them at Facebook for Developing Our Backend. So first, something about me, so you know who's talking to you. My name is Luka Sterbic. I'm originally from Croatia, but I moved to London about 3 years ago when I joined the Facebook London office. My team at Facebook works on a product for backend monitoring and stability. So basically, when one of our engineers sends a change, our system kicks off and tells them if this change is safe to land or not. And this is mostly built in Python. I do a bit of open source when I have time, and you can find me on github.com/Sterbic, and on Instagram, I'm at lsterbic. In case the resolution doesn't work well for the slides, they are already on my GitHub along with the code snippets, so you can get them from there as well if it's not great from the last few hours. So let's look at the agenda for today, because there's a lot of content. First, I'll talk about why is typing important in a modern Python code base and what are the benefits of using it. Then I'll cover an intro about typing. This won't be an exhaustive list of all the features available these days, but more of the 90% of features that you need to know to have most of the impact. The first section would be about types in the real world. How do you actually go about bringing typing to your either new or existing project? I'll explain what gradual typing is and how it helps to start typing large projects, and how can you make all work without breaking production. And the last section will be about some tips and tricks that I've learned about typing in Python over the last 3 years I've been working on it. So let's start with the question from the title. Why should I even care about Python typing? I mean, what's the point? Python has been running fine for decades now, really, without any statically typed information. But you also have to take into account the growing size of Python code bases across the last few years. Take Instagram, for example, that has millions of lines of Python Django code. That's a huge code base, and the win that bringing typing to such a code base brings is more readability and engineering productivity rather than the extra safety provided by a typed environment. Let me try to illustrate that on an example. So imagine you've started working at a big tech company. It's your first week, and you get assigned a ramp-up task by another engineer on your team, and your job is to log more information with each job submission. Then your senior engineer points you to this snippet that handles job submission and says you should log more attribute with each job. So how do you get started on a task like this? Basically, the first step is to even know what a job looks like if you want to log more information about it. So what can you figure out by just looking at the code? You can see that jobs is some kind of iterable, since we have a for loop over it. And you can see that each job has its name and a meta attribute that in turn knows about the priority of the job. But that's pretty much all we can guess from just looking at the code. So going by intuition, we could think that this job needs to be a class defined somewhere in my code base, so I can try to look for it. grep is my friend. I'll try grepping the whole code base for the prefix class job. The problem there is, though, on a large code base, even with a few thousand files, such common names can yield multiple heads. And even if you get above 10 grep results, it's usually not a good idea to try to scan them manually to figure out what you need. Another issue we need to keep in mind is that if we want to look for the usage of the submit function and then try to figure out how the arguments are constructed from there, is that we're not sure a priori how the submit function is called. It could be either import module and then module.function, or it could use the form syntax and just import the function name and call it just like that. In both cases, though, the names are fairly generic, so trying to search the code base for it by just doing a regex match will not yield to good results. Yet another issue in this case is even if we found a good candidate where the submit function is called, there's no guarantee that the argument construction is going to be trivial. It could again be buried 10 jumps away in a different module you didn't even know exists before you started looking at the code. So what else could we try? There is runtime analysis as well, of course. So with the type built-in function, we can check the type of an object at runtime, print its name, and with the dir function, we can actually expect all the attributes this job thing has. So by running this code, we'll know what the type of a job is, and what else can we log about its job. So basically, we're done. After this, we can just like extend the job function, the log function, and print some extra attribute. Yeah, the problem with this approach, though, is that it's quite clunky. For every piece of information you need to extract from your code, you actually need to be able to run it, which for a large application may not be as trivial as you think. If you have thousands or millions of lines of code, hitting a specific code in your whole code base with a single kind of top-level request to your application may not be as easy as you think if you're not super familiar with the app already. The other thing is that you need to instrument these few lines of prints for every single information you need to extract. And also, a drawback of this approach is that the experience of engineer does not play a role here. So you could be super senior with multiple years in the industry, and you'll use the exact same print statements as a new grad just fresh from university that joined your team last week. So there has to be a better way, right? And this is where typing comes into play. What typing basically allows is to make the input-output pairs of a function obvious by just looking at the code. The productivity win here is incredible because instead of searching and trying to guess what the job is, it's actually obvious from the code. And if we're using modern IDE, say PyCharm, for example, it's actually just one click away to check what the exact structure of jobs is. So it is a bit more code, sure, but it is actually more readable than the version with less code. Having more readable code will also help onboard new members in your team much quicker. Because if they're given this code as a pointer rather than the untyped version, instead of asking you, the engineer that created the task, or what this job is, they actually figure that out on their own and go to the next level and ask, okay, how do we actually use this? And this will cut down both on their time for development as well as your time helping them ramp up. So to sum it up, what typing your code achieves is to drastically cut down the time it takes from seeing a piece of code and starting iterating on it. So overall, you get your job done faster. Next, what I want to cover is if Python types are even Pythonic. When colleagues coming from statically typed backgrounds, say C++ or Java, hear that I'm working on Python typing, the usual reaction is, oh, wait, like, is Python now turning into Java? And like, is typing even like compatible with the Zen of Python? So let's try to look into that next. Are Python types Pythonic? I definitely believe so. And if you look at the Zen of Python with the famous import this, I think there are 3 points that support typing quite strongly. Explicit is better than implicit, readability counts, and in the face of ambiguity, it refuses the temptation to guess. Especially the last one is very obvious from the last example that I showed, because instead of guessing what job says, it's actually obvious from the code. So it really fits the Zen of Python really well. And if that's not enough, before he retired, Guido said so. He was one of the main authors on the PEP. So types are here to stay for a long time. In terms of comparison of Python and other statically typed languages, is it turning into Java or something similar? Not really. It's definitely learning from what other languages has done, taking the best bits and pieces that have a track record that proven they work, and kind of discarding what would slow Python down. Typing is still very much optional in Python. If you don't like it, you don't have to use it. Your code can be either 0% typed, 100% typed, or really anything in between. And that's the most common, to be honest. Typing in Python has no impact at runtime. Notice the asterisk. So this is mostly true. The only kind of performance drawback of using typing is actually importing the typing module, which is quite heavy. But you pay that cost only once per app restart. So as long as you're not restarting your server every few minutes, you will never notice the slowdown. And last but not least, typing errors can be ignored, especially if you're coming from C++, where you cannot compile your code if you have a typing error. In Python, you can actually encode silence the error and tell the type checker, leave me alone, I think this is fine, I'll fix this later, and the code will run fine in production without any issues. So next, let's look at how typing actually looks like on some examples. First, how did it even start with typing in Python? As you probably guess, like everything in Python, it did start with a PEP. The first one being 1307, titled Function Annotations by Colin Winter and Tony Lawrence. And this was back in 2006 even, when this PEP defines how to annotate a function, but not what those annotations mean. So basically defines the syntax, but not the semantics. This was done on purpose so that the community could quickly kind of iterate and play with annotations. And only many years later, the kind of final PEP was drafted to define type hinting in Python. And this brings us to the well-known PEP 484, titled Type Hints, by Guido van Rossum, the father of Python himself, Jukka Lehtosalo, which is the author of MyPy, and Luka Sterbic, which is a colleague of mine at Facebook London. So what PEP 484 basically took as the experience the community had accumulated with PEP 3107 and kind of finalized the type hints structure and also added some extra libraries and utilities to make typing easier and faster. So what needs to be annotated? Let's look at on an example. Here we have a function called myPrint, which accepts a message, just adds some brackets to it and prints it. And we have a square class that it's in constructor accepts the size of the A. So let's look at the typed and untyped version side by side. So as we just said, myPrint accepts a message, which in this case is a string, and returns none. While for the square class, we have the size of A, which is an integer, and by convention, all init methods have to return none. So the difference is this pretty much. So after each argument, we have a colon and the type of the argument. And the return type of the function is defined after you close the argument list and you put this arrow. So what else needs to be annotated? In some cases, variables. And the good thing is that you don't have to type every single variable in Python. Otherwise, the size of your code will probably double. So the type checker will actually ask you to type some variables where it's not sure on its own what the type of something is. So this is very common when, for example, you have an empty collection initialized in the init block of a class, and then it's filled somewhere else in another method of the class. The type checker cannot know of every single possible usage of that structure, so it will actually ask you to predefine the type. And this is done with this syntax where we basically say, okay, my dictionary is going to be dict with string keys and integer values. This syntax specifically for variable annotation works only in Python 3.6 and up, which you hopefully are on already. But if you are on Python 3.5 and down, you can still use the old type comment, which as far as the type checker is concerned, it's exactly the same. The only thing is that the newer form is obviously more readable. Now let's look at collections. On your day-to-day job, you'll probably be working with lists, dictionaries, and sets all the time. So this is quite important to know if you want to use typing. So here we have an example of a function that should just accept some parameters and return a list of countries where your application is running. So the first argument is a dictionary of countries keyed by int, which is the country code, and having string values, the country name as the value. The second argument is a list of active user locations, and this is expressed as a list, and each element of the list is a tuple with two floating point numbers representing latitude and longitude respectively. And the third argument is a set of strings with country names where your app should not be running. And with these three examples, basically you cover 90% of types collection you'll be using day to day. It's quite intuitive, really. You import the typed collection version from the typing module, and it usually has the same name as the actual implementation, only with the capital starting letter. So dict to dict, list to list. And you pass the types that the collection has inside the square brackets. Next, let's look at unions. Unions basically express that something at runtime can be either type A or type B. So in this case, I have an example that needs to fetch a Facebook object given its ID, so a numeric value. For simplicity, I've reduced it down to returning either a user or a page. So if you look at an example of how we actually call this, if I passed in my own ID, I'd get back a user object as expected. And if I passed in the FPID of the PyCon Japan page, I'd get back a page. And to express this with typing, we need to use a union, basically, because we cannot know just by statically looking at the code what our return type is going to be. Although, is this completely right? I think I forgot something, actually. What happens if I pass an ID that does not exist in the database? Let's say in this case, the function would return none if it didn't find an object. So how the correct typing for this looks like is then a union of user, page, or none. But this is a fairly common idiom, so there's actually a slightly better way of writing it, which is with the optional construct, also from the typing module. So this is considered slightly better compared to the previous example because it's closer to the semantics of your code, which is basically, if I find something, I'll return either a user or a page, and if I don't, I'll return a none, which is better expressed with an optional, and it's more clear than just doing a union with none. Although, as far as the type checker is concerned and implementation-wise, it's exactly the same. So an optional will always unwrap to a union with none. Last example in this section is with type vars. This is one of the more complicated aspects of Python typing, so I'll first try to explain the problem they solve, and then I'll actually show you how to use them. So let's start with this code snippet that has a base class and a derived class, which obviously derives from base class, and then we have a factory method. This is a quite common design pattern where a factory method will accept the class object or type or something, and will return an instance of that same type. So in this case, with the knowledge we have up until now of the typing, we say, okay, the input of this factory as a class of type base class. So this is how we say, instead of expecting an instance, we expect the type. And the return type is base class. So if we actually tried to call this with both the base class and the derived class, what the type checker is going to think the types of base and derived variables are both base class, because that's how we type the function. And that's where the problem is, basically. For the derived case, so the last line on the slide, what we actually want there is to the type checker to actually know that the return type there is going to be a derived class instance rather than a base class instance. So let's move forward. Basically, this is the case we want. With base class goes in, base class goes out, and derived class goes in, derived class goes out. And you can do this with type vars. Type vars you can think of as placeholders for a type. So the type, it allows you to express kind of dependencies in the input and output structures of something. So in this case, we say that the input is of type T, and the result is an instance of T. So by looking at the code, this is not like obviously better than the previous one, but the type checker can actually figure out that once the input type is materialized, so once it knows that the input is definitely derived class, then it will actually know that the returning instance is of derived class as well. And this code, compared to using a union, is going to be much easier to use, although a bit harder to write, because in general, you always want to have more specified return types, because then you don't have to if-else with is instance. Small note on how the type vars are defined. There is this T equals type var and again string T. This is an implementation detail, but important to note. The name does need to match, otherwise the type checker will complain about it. And the bound keyword argument is basically the most generic type that this type var can accept. So basically with T, you're saying this is something that looks like base class, but could be anything deriving from base class. I've mentioned the type checker quite a few times yet, but I haven't showed you an example of how to actually run it and what the results look like. So if you look at this code, we import the math module, and we have the square root function, and we call it both over an integer and over a string. As you probably know, the string version does not work out of the box. You need to cast the 100 from string to integer for it to work. Otherwise, it's going to throw an exception at runtime. So in this example, I'm using MyPy, which is the most common type checker used in the community these days. And we just run it by invoking MyPy and passing the path to the module we want to type check. And in this case, MyPy will correctly identify that the sqrt function has the wrong input type. It cannot accept a string. It expected a float. This concludes the examples I want to cover in Typing 101. I just want to give you a brief overview of some advanced topics that you can research on your own if you want to know more. The first one is forward references that you will need if you need to reference a class from itself. A very common pattern for this is when you have within a class a static method or a class method that needs to return an instance of the same class. So kind of a different format of the init, pretty much. And forward references are needed to solve that. Then there is the type checking signal from the typing module. And this one is very useful for breaking import cycles because of typing. So especially when you start typing larger code bases that were not written, thinking of types beforehand, you'll find that by introducing typing information, you'll create a lot of cycles that at runtime would not work fine. But just for the purpose of type hinting, they are totally fine. And you can usually mask the imports with this type checking signal so you don't run them in production. Next, we have the overload decorator that allows you to break down the usage of a function into multiple examples. So basically, if a function accepts a union of three types, you can actually break it down in 3 separate cases, each one decorated with the overload decorator to make it type check more nicely. And the last one I want to mention is Spire, which is a new type checker developed at Facebook that was open sourced at PyCon US earlier this year. And its main competitive advantage compared to MyPy is that it's much faster. For large code bases, it scales way, way better. So for Instagram, for example, it actually runs in 45 seconds on the whole code base compared to the 5 minutes that MyPy requires. So if you have a large code base and want to use typing, please give it a try. Now, we know why we should use typing and how to actually write the annotations, but now we actually need to check how do we make this happen for our projects. I'll start by covering the easy bit, which is the new projects. You're starting a fresh repo on GitHub and you want to get it typed. So how do you get things done? Basically, it's quite simple, really. From day one, you enforce 100% type coverage. No code should land without type information, and you need to make sure to enable the type checker in your continuous integration so that the progress you made does not go in vain and that the application stays type safe. And that's pretty much it. For new projects, the first step is Profit. Basically, you put in the effort, you added the types, you have the type checker checking each pull request automatically on GitHub and commenting back if it finds type errors. Next, let's look at the hard part, existing/large projects that you did not write and you don't own. So how do you get those? The first thing to understand here is actually gradual typing. You can't even kick off typing a large project without understanding gradual typing first. So let's look at an example. We have main.py, which depends on job and scheduler. Both the job and scheduler depend on utils, and the scheduler also depends on job to know how to schedule it. And then we have these examples from utils.py and job.py. So in utils.py, we just have a utility function to pretty print what we think is a job. It basically just dumps it as JSON with nice indents and prints it out. And then in job.py, we have this create job function that creates a job, pretty prints job created, and then returns a job. So obvious error here we notice, like we said, okay, pretty prints accepts a job, but we actually passed in a string. So at runtime, this will actually be fine, because a string can be JSON serialized. It's just going to be double escaped. So runtime will be fine. So the type checker should catch this. It's quite obvious. And if you run the type checker on this code as it is, it will actually not complain. And why is that? The type checker will not analyze any function that is not annotated. So in this case, create job does not have a type annotation, so the type checker will completely skip it. And this is what's called gradual typing. So basically, the body of a function is type checked only once its signature is typed. Job created. So if we wanted to actually type check this and catch this error, we'd need to change the signature of create job and state it returns a job. And in this case, the type check will correctly see that pretty print has an incompatible type. It expected a job and got a string. So this is how gradual typing works. But what's the motivation behind it? So basically, if you started off in a really large existing project, so a legacy, thousands of lines of code that you didn't write, are not super familiar with, and you want to start typing it, if without gradual typing, changing just a very simple utility function that you think understand what this code does, I can change the type, then would cause type errors across the whole code base. every single kind of usage of a utility function could actually type check incorrectly. And that's why gradual typing allows us to kind of pay this cost later. So when we type the utils module, we're actually gonna see errors only within the module itself. And then in a later point in time when we type job.py, we're gonna see type errors both relevant to job.py and as well against utils.py, which was type annotated earlier. And this allows you to pay the cost later in time, kind of delaying the errors to a point in time where a higher percentage of the code is going to be typed, and in theory it should be much easier to resolve them. So back on the plan for typing large projects. So we start off by typing common libraries, the utils.py of your project really. So this is modules that depends only on themselves and on a standard library and that are easy to type because they don't require a lot of context. So even someone fairly new on the team should be able to understand by just looking at the code and adding the typing information. Then you try running the type checker, you iterate until you get it to type check cleanly, and then same as for new projects, you activate the type checker in CI so that the progress you made does not go in vain. And say this got you to 5% coverage with types on your code base. How do you go from 5% to 100%? The most important next step is to ask people to add types to new code. Without support from your team, it's hard to get to 100% typed. Because when someone writes code, they're the best person to actually add typing annotations immediately. And that's the cheapest time in terms of effort to adding typing annotation as well. Even if you are the author of a piece of code, typing it immediately is cheaper than going back in a week, remembering what you did there and adding the type information. So you will need help from your colleagues to get this done. And it's also important to note that this kind of work needs to be rewarded by your organization. So it needs to be kind of clear in your team goals that you want to invest into code quality and better typing coverage. Last point here is to use MonkeyType to get a head start in terms of typing coverage. So what's MonkeyType? MonkeyType is a utility developed by Instagram that was open sourced about a year ago, and it helps types large code bases, which Instagram is one of the largest Django app in the world. So they soon figured out that typing millions of lines of code manually will not be a pleasant job, and it's quite repetitive, quite boring. So they found a way of automating out a lot of it. So what MonkeyType does, in a nutshell, basically, it collects types at runtime and logs them somewhere. It generates type stubs for your modules, and then it applies information back to your code. So basically magic auto type checking pretty much. I've mentioned a stub, but haven't shown an example of it yet. So this is what the stub for the math module from the standard library looks like. It's basically just a list of module variables and functions with type information, but without the implementation. So you can notice, for example, for the last function, 8 and h, returns a float, and the implementation is 3 dots. This is actually not an abbreviation. This is valid Python syntax, and it's the preferred way of saying this is just kind of typing information, has no body, do not use it. So how do you actually use MonkeyType? First, you need to pip install it, obviously. Then you run the MonkeyType run wrapper with your application. This will introduce some changes in your application and will inspect every single function call and log types by default in a SQLite-free database in the current directory. And once we have this information, we can ask MonkeyType to generate a stub for the module we care about. And in this case, for the utils example I had before, it's going to say that prettyprint accepts a job that's a string. Why is that? Because that's the only usage we had in the code. So although we think this is incorrect, the actual code think it's right, because the only instance it saw was of prettyprint being called by a string. And the last step is to ask MonkeyType to basically take the generated stubs and apply them back on your code. These 4 steps allow you to kind of automatically generate typing information for your code. And this can get you a head start once you want to start typing a large project. It's far from perfect, obviously, and it cannot sometimes generalize correctly, but it can get you to 10, 20, 30% quite quickly and quite easily, almost all automated. One note here, though, is running any application with MonkeyType makes it much, much slower. So running it on 100% of production requests would not be feasible. So you can either run it in a development environment, like have it run with shadow traffic and just collect typing information, or you could have a very small subset of production machines actually run it. And this is what Instagram does, basically. They sample a very low percentage of requests and run them with MonkeyType. The last section has some tips and tricks. So the first one I want to cover, and I think it's the most important one as well, is how does duck typing work in this new statically typed world of Python? So we all know the famous, if it looks like a duck, quacks like a duck, and swims like a duck, it's probably a duck. But then with statically typing, this doesn't really work, does it? As usual, let's look at an example. Here we have this duck things function that accepts a duck and just calls quack and swim over it. Then we have 2 types of ducks, farrier duck and gecko duck. They both quack, they both swim. So at runtime, you could actually pass an instance of either of those into duck things, and things would work fine. This is what the ducks look like, by the way. The problem is with type checker, though. Since neither of these subclass directly from the duck base class, the type checker will just complain this doesn't work. So effectively what it looks like, if we try to pass an instance of farrier duck, although it would work fine at runtime, it says, no, it does not subclass from duck, I do not want to accept this. So how do I fix this? With protocols. And this is what it looks like. So protocols in Python typing are similar to, say, interfaces in other languages like Java. So it basically defines what an object should look like without having any implementation. So here we say that a duck is a protocol that knows how to quack and how to probably swim, okay? And in this case, we'll actually fix our previous example because protocol allows you to do, instead of nominal subtyping, doing structural subtyping, which basically says instead of like directly subclassing from duck, something is compatible with duck, just it has all the methods defined in the duck protocol. So this is how you get duck typing in a statically typed world, which is quite powerful, to be honest. Second is the typeshed. If you have an error typing against the standard library and you try to look at the code for the standard library to figure out where the problem is, you'll actually notice that typing information is not part of the standard library. It's actually in a separate repo called the Typeshed. And this repo is bundled with your type checker, so either MyPy or Pyre. And this is done so that the typeshed can develop much faster. It's not bound to the Python release schedule, but it's actually released fairly often, I'd say even on a weekly basis. And it's still very far from perfect, to be honest. So send a pull request if you find the problem. And in my experience, it gets merged within 1 to 2 days. Common areas that are still kind of less typed are multi-threading and multiprocessing, especially. So if you have typed multiprocessing code and you see errors, it's safe to assume that maybe something is not typed perfectly in the typeshed. Last example here is type ignore, which is the comment that you can use to silence typing error on a single line. And this is something that's very Python specific. There's no kind of equivalent in statically typed languages that basically allows to say to the type checker, although you think this line is wrong, I'm sure it's right, just leave it there and continue. And it's not necessarily evil. So sometimes it's actually fine to use type ignore, although it kind of hides an error. And I want to bring up here a discussion I had with Guido a while ago when I wanted to type part of the Q module, and he was against it because I was exposing kind of internal implementation details just to have my application type check correctly. So in his opinion, typing, especially in the Typeshed, should be very close to the documentation rather than trying to get it done perfectly. So the actual example we were discussing in that case was for the Q module that needed this unblock Q callback, because if you have a join call on the Q, you cannot timeout on it. So basically, the my timeout thingy, which is a context manager, needed to unblock the queue once the timeout was up. And to do this, what I needed was access to all tasks done, which is basically the top level mutex for the queue. And to say like, okay, once the timeout fires, just kind of notify all that we've given up on these jobs and just cancel them. And this is not typed correctly in the Typeshed. It actually does not have at all the all tasks done variable. And the correct solution here, if you ask Guido, is to use just the type ignore comment to silence this error rather than adding a fairly low level implementation detail to the Typeshed. Okay. So let's just sum up what we learned today. Typing annotations are indeed Pythonic, and Python's not turning into Java. Start using them for the readability win and the productivity that your engineers are going to have, and get the extra safety of a type checker pretty much for free in this case. For new projects, it's quite easy. You just get started with 100% typed from day one. You activate the type checker in CI, you're done. For large projects, it's a bit harder, but still very much doable. You can start small with gradual typing by typing the utils.py of your project that are easier to understand. And you can use MonkeyType to get a head start of the easiest bit of code. So the slides and code snippets for all the code I showed are already available on my GitHub on pycon-jp-2018. So check it out, and I think we still should have a few minutes for questions. 2 minutes.
Hello, thank you for the presentation. My question was about, in unit tests, frequently we use mocks. How do you convince a function that's typed to accept your mock without spending too much time defining what, for example, the protocol should be? Thank you.
So, I mean, you'd have problems with mocks only if you type check your unit tests, which I usually wouldn't advise exactly because of the case you said. I know there's some work on making this easier, but I don't think there's anything I've seen recently that went in that direction. So for my team, at least, we don't type, except for like super trivial stuff, we don't type check mocks. At some point, I think mocks are going to be kind of treated separately by the type checker, but it's not yet the case.
Thank you. Does anyone has no question? Okay, thank you very much for your talk, Luka.